So how do we evaluate the heat transfer in a bundle of tubes? Let's say we have NT number of or NL number of rows of tubes, and each row has NT number of tubes in each of them. And this is the correlations that we find the average Nusselt number for the system. And we said PRS is evaluated at the surface temperature of the tubes, but the other properties are all evaluated at the average temperature between the inlet and outlet. Now for this bundle of tube, we often know the inlet temperature, but we don't know the outlet temperature. So the process for that is iterative, and the steps to do the analysis for the bundle of tubes is first we evaluate properties at the known temperature of Ti. So we know the inlet temperature of fluid. We evaluate that one. We use the correlation that we have for the average Nusselt number, and from there we can estimate the heat transfer coefficient. So we can estimate H. And from there we estimate the temperature of fluid leaving the tube bundle. The way that we are using this relationship, Ts minus To divided by Ts minus Ti. The ratio of temperature is going to be exponential of minus pi d n h, and it's the total number of tubes, and rho v cp nt st. And this is the indication of mass. So this is the m dot cp, and this pi d n h is in fact H average times area. So this is how we got this equation. We will see that later on, but all the properties, like this is the properties of here, everything are getting evaluated at free stream temperature. So we find properties at Ti, estimate H. We use the H here in this equation, and other one rho and C for at the free stream temperature, and then we find the value of To. Now that we have using To and Ti, now we calculate another temperature what we called log mean temperature difference, or LMTD. And we will see that later on when we are discussing the heat exchanger. We evaluate this log mean temperature difference to evaluate the rate of heat transfer. In brief, using this temperature difference gives a better estimation of the heat transfer. So this delta T LM or LMTD is Ts minus Ti minus Ts minus To natural log of Ts minus Ti, Ts minus To. When we find this delta E, the LMTD, the temperature, then last step we find the heat transfer rate. Generally, we evaluate that per unit length of tubes. So the way to do that is this Q prime is Q over L, where L is the length of the tube. This is length of tubes. And this is going to be H and P D. Of course, if we had L, it would have been just the area, but now we are in Q over L times delta T L. So this is the way that we find the heat transfer rate. Now, we may want to evaluate properties. So we may want to do the iterations, finding this TO. We want to do the evaluate properties at the TO plus TI divided by 2 and repeat the calculations till the difference is very small. But sometimes we find that the properties does not really very much change from TI to TI plus TO divided by 2. Depends on what would be the outlet temperature. So going through this iterative process, we can find out the best estimate for the properties, or finding properties at the average temperature of inlet plus outlet.